Hey guys, I hope you're doing well. We're moving on to the next gas law for this week. This one, I know it looks like it says gay, but it's actually pronounced Guy Lussac's law. And this law is going to be the relationship between pressure and temperature. So you have a Nearpod again this week. I feel like it's just easier for us to do it this way. I appreciate any feedback that you guys may offer. Also, please reach out if the video is not helping you and you need like a one-on-one explanation. I haven't really gotten anybody reaching out, and you guys are doing pretty well according to the data that I've been collecting, but just reach out if you need help. So I'm gonna get started. If you like the notes that I had been providing for you all year, I've been putting the templates multiple places in Google Classroom, and if you can't find them, just let me know. I know it helps to like kind of keep your thoughts organized. If you like taking notes on your own or jotting things down your own way, that's fine. So Guy-Lussac's law is a direct relationship. So we already been practicing indirect and direct. Basically, they do the same thing. If they're going to increase, if one increases, the other increases. If one decreases, the other decreases. So they do the same exact thing. This is just reiterating that as temperatures increase, pressure will also increase. These laws are only accurate if volume is constant. So if volume's moving around, then this law would not apply. So again, if temperatures decrease, the pressure will also decrease. What happens is that temperature is being increased, so this is causing the molecules to get really excited. So they start moving a lot faster, and that means they're impacting the walls of the containers more. So they're hitting the sides of it. This is causing a lot of pressure. There's not enough room for them to continuously like keep hitting things, bumping into each other. So that's where the pressure comes from. So what we know so far is that pressure divided by temperature is going to be equal to the constant K. And we know that pressure 2 divided by temperature 2 is also equal to the constant K. So since K and K are equal to each other, our formula for Guy-Lussac's law is going to be pressure 1 divided by temperature 1 is equal to pressure 2 divided by temperature 2. So there is a problem in here. I'm not going to really spend time on this one. This one's more if you can just learn from the slides and don't need me narrating what's happening. I'm going to go forward to the videos because it's all solved for you here. But I'm going to go to the videos that I made so I can show you exactly what's happening with the formula. So when we're manipulating the equation, this is going to allow us to solve out the equation before, I'm going to pause the video, solve the equation before actually plugging things in. It makes your job easier in the end. If you like plugging things in and then manipulating the equation, that's fine too. But I think this way is easier, so this is the reason that I chose to show you this way. So what I mean by manipulating the formula is we're trying to isolate a variable in this formula so that it's easier for us to work with at the end. So in this case, I'm giving you an example. We're looking for pressure 2. We don't know what pressure 2 is, so we need to isolate it. So what we need to do is get rid of this T2. So what we would do is, because it's being divided, this little fraction it's on the bottom means it's divided. The opposite is multiplication. So we're going to multiply by T2, and we're going to do that to both sides in order to get rid of this T2 on the right. So when I do that, what's going to happen is these T2s, because they're opposite of each other, they will cancel out. We already know that from all of the dimensional analysis we've been doing. So that's going to leave us with T2 times P1 over T1. This is really good because it frees up our P2 to be alone. And when we have this alone and we plug everything else in, it's just going to be easier for us in the end. The formula's already been changed so that P2 is going to be the variable that we're looking for. So that's if we're looking for P2. Super simple. If we're looking for T2, things get a little bit more messy, but it's really just one step more. So I'm going to show you what I mean by that. So in this case, we don't have temperature 2, so we're looking for temperature 2. We're going to go ahead and do the same steps right now, which is getting T2, because right now T2 is at the bottom, so it doesn't allow for like the easy manipulation like the P2 did. So we need to get this T2 on the top. So what we're gonna do, or not on the top, just not be, just not be on the bottom of the equation. So what we're gonna do is we're still gonna multiply by the T2 to get it rid of it, get this P2 alone. The reason that we do that is because it frees up the T2 from the bottom of the equation, because then that would mean that the unknown would be at the bottom, and it's really difficult to work with the equation that way. So we want the T2 on the top. So what we're gonna do next is, our goal is still to isolate this T2 because we're looking for a T2. So we have to get rid of this P1, T1. So if you remember from algebra, the way to get rid of a fraction is to go ahead and multiply by the reciprocal. So what reciprocal means is just flip the equation around, or the fraction, I'm sorry. Flip the fraction around. And I'll show you in a second what this is gonna do. I'm just kind of writing them on both sides right now. Because remember, what you do to one side, you have to do to the other, just basic algebra. So what that's gonna do is it's gonna put T1 opposite of T1 over here. So we already know that when things are opposite of each other from dimensional analysis, they cancel out. And that also puts the pressures opposite of each other. So now we have this T2 alone because everything on this side has canceled out, and that's what we wanted. Over here on this side, the P2, T1, P1 is gonna stay because there's nothing for it to cancel out with. So we've already accomplished our goal of isolating this T2. So our formula is gonna be T2 equals P2 times T1 over P1. If I was you, what I would do is I would just write down these formulas that we've already manipulated and solved for you. That way you don't have to do it every single time. Just keep it in your notes that if you're looking for P2, what's the formula? If you're looking for T2, what's the formula? And keep them in your notes under Guy Lussac, wherever you have it. That way you don't have to keep manipulating the formula over and over again. But this is just like behind the scenes, like why is this the formula when you're looking for T2? Why is this the formula when you're looking for P2? And we're usually looking for P2 or T2 because we already know the initial and the initial pressure and temperature. And it's usually like if this were in the lab, we would know what the original pressure is and what the original temperature is. And we would be testing for pressure and temperature, and we would be using this formula to predict what we were going to get in a lab setting. So I'm going to give you two examples really quickly, just using what we just did. So this question is asking, is saying that a gas thermometer measures temperature by measuring the pressure inside a gas at in a fixed volume container. A thermometer reads pressure at 248 kilopascals. So I'm using context clues. It says pressure, so I know it's pressure. And it says at 0 degrees Celsius. We should know already by this point that degrees Celsius is a temperature. What is the temperature? It's literally asking you, what is the temperature? So you know that you don't know the second temperature. So you're missing T2. When the thermometer reads a pressure of 345 kilopascals. Just know that kilopascals is pressure. You have to just memorize that the unit kilopascals means pressure. So that's your context clue for that. So in this case, we're looking for T2. I was gonna rewrite the whole formula, but I don't think I have enough space. So we're looking for T2. If you were smart or very crafty, I guess, you would have already written down the formula so you don't have to manipulate it. So we know that T2 is going to equal P2 times T1 over P1. So hopefully you just already wrote this down and you're not having to manipulate the formula as you go. No point in doing more work. And now it's our turn to just plug in. So if you were doing what I did earlier, which is identifying your givens, this is super easy. All you do is plug things in where they go. So we already know that P2 is 345 kilopascals. We don't have to include the units because both of our pressures were in the same unit. And now we can move on to T1. T1 we've already identified, but we're running into a little problem. It's in degrees Celsius, and you know when you're using these gas laws, you cannot use Celsius. We have to convert to Kelvin. So very easy, very simple. If you are given a temperature of 0 degrees Celsius, all you have to do, or anything for that matter, whatever your temperature is in degrees Celsius, all you do is add 273, just labeling that this is for T1, which was 0 degrees Celsius, add 273 to it, and you've already converted to Kelvin. So 0 plus 273 is 273 Kelvin. You might want to do that before you start plugging things in also. So 273 is going to be on the top because that's our T1. Now we're going to go back and we're going to plug in our last variable, which is our P1. So we already labeled everything. We had P2, so P1 is up here. Just make sure that you're putting the right pressures in the right place because you were given 2 pressures. So it would have given you a different answer had you switched them around. So make sure when you're labeling that you're labeling appropriately, initial and final. So 248 goes on the bottom. Because this is already solved for T2, all we have to do is do 273 divided by 248 and multiply by 345. And that gives us 379 Kelvin. When you're explaining something to people, they're not going to understand what Kelvin is. So what we usually do is we convert back to Celsius. So if converting from Celsius to Kelvin is adding 273, converting from Kelvin to Celsius is going to be subtracting 273. So subtract 273, and that is going to convert this problem into degrees Celsius, and which is something, I mean, we know what Celsius is. Usually it's like common language. People know what Celsius is. So 106 degrees Celsius is our answer. So that's how you do a problem where you're looking for temperature. So we're going to go ahead and work through our last example. And this is going to be, we're looking for pressure 2 in this example. So the temperature of a sample of gas in a steel tank at 30 kilopascals. So this is going to be our pressure. Kilopascals is a unit of pressure. Is increased from negative 100 degrees Celsius to 25 degrees Celsius. These are temperatures. So we have our that should be T1, I'm sorry. Let me change that. So we have our initial temperature, our T1, and our final temperature, our T2. And now it's asking what is the final pressure. So I noticed that these are in degrees Celsius. So right away, I'm just going to change them into Kelvin because I know that I can't use degrees Celsius. So negative 100 plus 273 is going to be equal to 173 Kelvin. So our T1 is done. I'm going to move on to our T2, which is 25 degrees Celsius. So we're going to write down 25 degrees Celsius, or not degrees Celsius, you can leave that off. 25 degrees plus 273, and that should give us 298. And these are done. We've converted to Kelvin. And because we're looking for final pressure, we're not going to have to do any more temperature conversions in this problem. So we're looking for P2. P2 is an easy one because all we had to do to get this P2 alone is multiply by T2 on both sides, isolating that P2. And what would happen over here with our T's is they would cancel out because they are opposite of each other. One's on top, one's on bottom. So our equation would be P2 equals T2 times the fraction P1 over T1, and we're dividing between those two. And easy part is next, which is plugging in. We've already identified all of our givens, so this part should be easy, and we've already converted. So T2 is 298. Make sure you do the right one. We labeled this one T1, so that's why I didn't write that number down. So T2 is 298. Gonna draw in our P1. P1 is 30 kilopascals. We don't have to convert or do anything. All we do is plug in. And that 30 is gonna be above our T1, which is 173. And now we're ready to just plug this into our calculator. So I like to do the fraction first. It's easier, it makes more sense to me. So I do 30 divided by 173, get the answer for that, and then I multiply by 298. So this is gonna give me 51 kilopascals because this was P2, so it was a pressure. Pressures are usually measured in kilopascals. So we're done with this example now. Notice that the P2 is very similar to the P1, like they're close to each other in numbers. So if you get something insane like 2000 or 0.00006, you know that you did something wrong. So remember with these, because they're either direct or indirect relationships, they're proportional to each other. So they need to be kind of in the same range. So those were your examples to use. All I did was give you guys 4 problems to practice with. It's gonna be matching, so you're gonna be given the answers and problems, and you have to just match them up, just like if this were a card game. You're gonna need a calculator and scratch paper. Your phone works great as a calculator for these problems. I use my phone to do these. Remember to convert back to Celsius from Kelvin at the end, and the way that you're gonna do this is basically just subtracting 273. And this is what the game is gonna look like. Oops. You're gonna have problems. These are your problems right here. You're gonna have an unknown, so wherever your question mark is, that's your unknown, and you have to match it up with the correct answer. There's only 4, so see 1, 2, 3, 4, and then you have 4 answers. And that is gonna be, I don't know why it keeps going back. That is gonna be your lesson for today. Please reach out to me if you need help with anything or you're not understanding. Even if it's on old stuff, like you want help on the stoichiometry stuff, I'm available. This next week we'll finish up the last couple laws, and then you guys will have extra credit after that. So let me know if you need help. Have a good week. Try to get everything done before Friday so I can have updated grades. Bye.